Okay, so today we're going to be talking about the structure of matter and how atoms actually form compounds. And in particular, we're going to be talking about covalent bonding and metallic bonding. So compounds, what exactly are compounds? First of all, compounds are when you have two or more elements of different types combining to form something new. So that means you have to have a chemical change. If you have a chemical change, that means you have new properties. So that means that the substance isn't the same as it was before. It has different melting point, boiling point, different reactivity, all of that kind of stuff. So these atoms form different bonds, and a chemical bond is just some kind of attractive force that holds different atoms or ions together. And there's different types of bonds. We've already talked about ionic bonding, and now we're going to talk about some other as well. So compounds have to have specific ratios of atoms, all right, which means that you always have the same ratio or the same format, okay? And they're written in chemical formulas like these that you see here. This is water, H2O. Water always has two hydrogens, that little subscript 2, for every one oxygen. Otherwise, it's a new compound. And then the same thing for the sugar here and for sodium chloride. That's salt. For sodium chloride, you always have one sodium ion bonding with one chloride ion. And the ratio is always the same. And again, if you have a different ratio, you have a different compound. So the chemical structure actually shows you how atoms are going to be arranged in the compound, or how those atoms or ions are connected. And in order to specify a chemical structure, you have to know your bond length, which is your distance between the nuclei of the atoms, and you have to know the angles between the atoms. And you'll go more into that in chemistry. So what are molecules exactly? So we've had the word compound. We know that that's just two different elements that are bonded together, two or more. Molecules are when specific atoms are joined together, and they don't have as strong of attraction as ions. Okay, it's usually between nonmetals only. They have low melting points and boiling points. And these are things that we typically know as gases or liquids that are coming together. Okay, if there's a stronger attraction, then you end up having a higher melting and boiling point. So bonding is just when valence electrons interact. Remember, the whole point of bonding is to stabilize the atoms so that they achieve that full outermost energy level or full valence shell. And there's two ways that you can do this. You can share electrons through covalent bonding, or you can transfer those valence electrons in ionic bonding. And we've already spent a lot of time talking about ionic bonding and how metals transfer or donate their electrons to nonmetals. And I've put a little overview of a video link on here that you're more than welcome to go to, and you can see the different types of bonding, and it goes over examples, gives you some animations and that sort of thing. It's really good. I would suggest you watch it. So first of all, since this is all about valence electrons, in order to keep track of everything, we've got to make sure that we know about those valence electrons. So just a little review. Remember, atoms in the same column or the same group have the same number of outer electron configuration, which means they have the same number of valence electrons. And remember your group numbers, 1, 2, 13, 14, 15, 16, 18, so on and so forth. Those are your cheater way to remember how many valence electrons you have. Remember, when you get over to this side, 13, 14, 15, 16, 17, and 18, you cut off the 1, and that tells you how many valence electrons you have. So this is just a little visual of your groups on the periodic table. Group 1 on the periodic table, the alkalis, have 1 valence electron. Group 2, the alkaline earth metals, have 2 valence electrons. And then we come over to this other side, and there's one exception, okay? Remember, helium up here is very tiny. It's in this first period, this first row. And because it's in the first row, It only has electrons in that first energy level. And remember, this first energy level only has room for 2 electrons. So helium, even though it's in group 18, it only has 2 valence electrons. It doesn't have 8 like all the other noble gases that are in group 18. So all the other noble gases do have 8 except for helium. It's the exception to the octet rule. It only has 2. Okay, so just a review about ionic compounds. Remember, this is between metals and nonmetals. They make a crystalline lattice structure. That's why salt looks like little crystals. They have a repeating arrangement of their ions. They are very strongly bonded, okay, which means they have rigid structures, and that means that they have high boiling points and melting points because of those strong forces between the ions. So it takes really high temperatures to get these substances to melt. This is an example of that lattice structure that you would see in, for example, salt. So it makes very regular shapes like cubes. Okay, so remember the opposite charges are what causes these things to attract. So when the metals give away, they become positive and they get surrounded by the negative ions. Okay, and it's always a repeating pattern. However, they're brittle, which means that even though they don't, even though they're strong, they will break, and we'll go into why they break in a little bit later. Okay, so do these guys conduct electricity or heat? No. In a solid form, ions are locked into place into that lattice structure, so they're insulators as solids. However, when you melt them, the ions can move around, and because they can move, that means charges can move, and that's what actually causes electricity. Okay, so melting ionic compounds, when they're in their liquid state, they can conduct, or if you dissolve them in water. But remember, they have really high melting points, so that's super, super hot, way hotter than just putting it on the stove. Okay, so the quickest way to get an ionic compound to conduct electricity is to put it in water. So if you put salt in water and then you hook it up to a circuit, you can actually cause electricity flow. And this is why they say don't use things like hair dryers and that sort of stuff around bathtubs, because bathtubs don't have just pure water in them. They have ions. There's salts and other minerals in there, and so you can get a charge and you can electrocute yourself. All right, so metallic bonds. What exactly are metallic bonds? We're going to go into this briefly first before we talk about covalent bonds. Metallic bonds are where you have metals that are being, metal atoms that are being held together, okay? So metals, you need to understand, don't actually hold on to their valence electrons very well. They hold on to them pretty weakly, which means, because remember metals don't like their electrons, they want to give them away. You can kind of think of metals as having a bunch of positive ions or cations floating around in a sea of electrons. So what ends up happening is it's almost kind of like a ping pong game. A metal atom doesn't want its electrons, so it gives it away, and it ends up going over sort of to another metal atom, but as soon as that metal atom gets that electron, it bounces off as well. So you almost have to think of these guys as little, the nuclei of the atoms, the positive part of the atoms kind of floating around in the middle of these valence electrons, and we call it a sea of valence electrons. And I've also put a link on here to a video about metallic bonds that really shows this well, shows how the electrons easily come off of the metal and how they will kind of float around in this sea around the cations. Alright, so this is sort of a visual, a still visual of what this looks like. This is where you have your positive portion of the atom, so the outer electrons, those valence electrons, have left, and that's what the little blue guys are here. And so these electrons just can kind of flow around, they bounce around inside here, they go all over the place from atom to atom to atom, moving everywhere, okay? And that allows them to move through the solid, and this is why they're such good conductors of heat and electricity. So if I put a flame over here on this side and I add some heat, the electrons, because they're moving around and bouncing around, are going to then transfer that heat to these other atoms, and the whole thing gets hot very quickly. And the same thing is true for electricity. If I put this up to a charged portion here, like a socket, which you would never want to put metal in a socket, but if you put it in a socket, all of a sudden all these electrons are going to move through the metal, okay, because they are going to be moving with the rest of the circuit, and so they conduct electricity very well as also. Okay, so what else about metals? Metals are considered what's called malleable, which means that they can be hammered or bent into a thin shape, and they are also ductile, which means they can be drawn into wires. Now, how is this possible? Okay, why this is possible is because, again, of the sea of electrons. Those electrons can slide around and move around everywhere. So you can always have electrons kind of in between these positive cations so that they don't get repelled. And so if I was to hit this to try and bend it, hit it on the side here, it would cause it to slide over. Okay, so because the electrons can slide, you never have two positives touching each other, and it just slides and bends. And so this is why you can bend a paper clip without breaking it and that sort of thing. Alright, so if you remember back to what I said earlier, I said ionic compounds are very brittle, which means they break easily. So if I was to do this same situation with an ionic solid, hit it right here, how is that different? Well, remember, these electrons don't actually move around. The positive metal has given the electrons over to the negative nonmetal, okay, forming a cation and a negative anion. These anions don't want to get rid of those electrons. Those electrons can't just slide around anywhere inside of here. So if I hit this on this side, what ends up happening is you end up with two positives next to each other, negatives next to each other, and you have a really big repulsion there. Remember, positives don't like to be next to positives, and negatives don't like to be next to negatives. And so it causes it to split or break apart. Okay, so when you hammer an ionic compound, it breaks. If you hammer a metal, it will actually bend and move. It has that malleable ability, and it's because those electrons can move around on them, and with ions they can't. Okay, now the rest of the time we're going to be talking about covalent bonds. Alright, covalent bonds are bonds between typically nonmetals, and nonmetals like to hold on to their valence electrons. Remember, they need more, okay? So they can't give the electrons away to bond, but they still want a full outer shell. So how do we get around this? Well, we get around this by sort of playing a little tug-of-war and sharing the valence electrons between two nonmetal atoms, okay? So since they both share them, they get to count the electrons to get towards their noble gas configuration, or that full valence shell. And remember, that full valence shell that we're trying to get to is the magic number 8 for almost all elements. Alright, so doing a little example here. We have fluorine. Fluorine is in group 17, so it has 7 valence electrons. And so when we do our Lewis dot structure for fluorine, we have 7 dots around it, and those represent those valence electrons. Okay, and through a covalent bond, if we were going to have fluorine bond with fluorine, okay, which fluorine is extremely reactive, it is the most electronegative element there is. It does not like having only this 7 on here. Alright, and so we've got a second fluorine on here. What's going to end up happening is these electrons here that are by themselves are kind of going to share between them so that they can stabilize their outer shell. Okay, so what does this look like as far as a Lewis dot structure? It looks like these electrons right here in between the two fluorines are kind of in between them, and so if you count around each fluorine you have a full energy level. Okay, this double dots represents the covalent bond. Remember, it's a sharing of electrons, so they're kind of playing this little tug of war, and the electrons are kind of going around in those shapes. Remember, they don't actually go around in orbits or rings, okay, but they're bouncing around in these little shapes, and basically what ends up happening is they kind of bounce back and forth in between here, and so sometimes they're closer to this fluorine and sometimes they're closer to this fluorine, but these guys kind of get shared between the two so that for, most of the time both of each fluorine atom are happy. Okay, so if we look, we've got 8 around this fluorine, and if we look at the other one, there's also 8 around it. So again, they both end up with that full energy level or valence shell. That's the whole point, is to get that full energy level. That's why we bond. Okay, so we want to have 8 electrons for them to be happy or filled. Okay, so remember, that's the whole point. All right, so how do we recognize these different bonds? A single covalent bond is 2 valence electrons being shared, 2 dots, okay? And this occurs, again, remember, between nonmetals or also hydrogen. Remember, hydrogen's weird. Even though it's over there in group 1, it's a nonmetal. It's not an alkali metal, okay? So hydrogen occurs, and then all of our nonmetals over on the right side of the periodic table as well. Okay, these are different from ionic bonds because these form molecules. Okay, so molecules, remember, you got to think of them as being covalent bonds. All right, so we've got 2 specific atoms that are being joined, or more than 2 specific atoms that are being joined together, but between the atoms it's always 2 that are sharing these electrons. Okay, in an ionic solid, you can't tell which atoms the electrons have moved from or to. You just know that the metals wanted to give their electrons away and the nonmetals wanted to take those electrons, but you don't have a specific atom that one went to the other one, okay, to make, for example, salt. But in molecules and in covalent bonds, you know exactly which atoms are sharing what electrons with each other because it's always between 2. Okay, so how do you actually show how these things are formed? Okay, you got to kind of think of it as a puzzle, and you have to know what your formula is, and then you put those pieces together to make sure that you actually have the right formula. So, for example, water. Okay, if we look at water in more, we know that hydrogen has 1 valence electron. It's in group 1. And so we know that hydrogen wants 1 more. Remember, it only wants 1 more because it's super tiny. It's in that first period, so it only needs 2 electrons to fill its shell, its outermost shell, because it only has that first energy level. All the other elements, except for the ones in the first row, except for hydrogen and helium, remember, they want to have 8. Oxygen has 6 valence electrons because it's in group 16. It wants 2 more. If we look, we've got paired here and paired here, but this one, not happy, doesn't have another one, and this one doesn't have another one. So these are our holes. These are our unoccupied spaces around the oxygen and its outer energy level. Okay, so these guys are going to end up sharing to make each other happy. Again, they don't transfer, they share. Alright, so we start putting the pieces together just like a jigsaw, okay? So we stick our hydrogen over here next to our oxygen, and now if we look at hydrogen, hydrogen now has 2 electrons that you can think are kind of zooming around it because this one here from oxygen is kind of being shared, okay? And that one from hydrogen is kind of being shared. But oxygen still only has 1, 2, 3, 4, 5, 6, 7. It's not happy yet. It still needs 1 more. This little space over here is empty. Alright, so what do? Well, bring in another hydrogen. Simple as that. So we have a second hydrogen that attaches to the oxygen. And now if we count around oxygen, everything is full. 2, 4, 6, 8. It's happy. okay? And each hydrogen is happy because each hydrogen has 2 electrons. Okay, so remember hydrogen only needs 2, so all of our energy levels are full for every atom on here. And so we have made everybody stable and content. Okay, so sometimes in order to stabilize the atom, we need to share more than one pair of valence electrons. Okay, and that's just to make sure that everybody has a full shell. So instead of a single bond where you only have 2 electrons being shared, you can have double bonds, which is where you have 2 pairs of electrons or 4 total electrons. Or you can even have triple bonds, and that's when you have 3 pairs of electrons or 6 electrons total. Okay, so this is just to make everyone have their full shells and be happy with 8 around them. Okay, so let's do an example of that. Carbon dioxide. You guys have all heard of carbon dioxide. This is the stuff you breathe out. Okay, so first of all, carbon has 4 valence electrons because it's in group 14. I'm telling you carbon has to be the central atom, and the reason why it has to be the central atom is because it's got the most holes. Okay, so carbon is almost always in the middle when you're covalently bonding. It wants 4 more. It's got 4 holes here that it wants to fill. Okay, it's trying to get to 8. Oxygen is in group 16, so it has 6 valence electrons. It needs 2 more for its valence shell or outer energy level to be filled. Okay, so how exactly do we take care of this? Well, let's start putting the pieces here, just like we did for water. Okay, if we attach 1 oxygen to the carbon, we've got these 2 electrons that are being shared. Okay, no one is happy yet because oxygen still needs 1 more electron over here to be filled, and carbon needs 1, 2, 3 more electrons to be filled. Right now around carbon we have 5. Okay, right now around oxygen we have 7. So we're still not filled or happy yet. Okay, so what do we do next? Okay, well, try attaching another oxygen. Okay, if we attach a second oxygen, all right, we still have an issue. Okay, this oxygen still has 1 electron that it needs. It has 7 around it. And carbon is still not happy because it still has 2 electrons that it needs. So right now it has 2, 3, 4, 5, 6 around it. So we still got 2 holes here. But if we look, we got a hole here on this oxygen and we got a hole here on this oxygen. We've still got 2 electrons here that carbon is not happy with as well that aren't being shared. Okay, so at this point, what can we do? Okay, the only option is to just do some more sharing. Okay, so if we do some more sharing, we can get all of our electrons to be around each atom. Remember, they're bouncing kind of back and forth here in these spaces, and everyone can share and be happy. Okay, so here's that 1 electron over here from the carbon, and here's that other electron there from that carbon that isn't paired. Here's that electron around oxygen that isn't paired, and that other electron around oxygen that isn't paired. And we can bring those guys in, and we can just share again. So now, instead of having 1 pair of electrons that are being shared, we have 2 pairs of electrons that are being shared. And remember, any of those that are being shared, we can count for both atoms, okay? All right, so in order for this to happen, we've had to make double bonds. And we've actually had to make 2 double bonds, okay? Remember, each atom gets to count all of the electrons in the bond. Sorry, this should say electrons, not atoms. Okay, so if we count around oxygen, we got 1, 2, 3, 4, okay, 5, 6, 7, 8. These 4 here are in those covalent bonds. We have a single bond here and we have another single bond here. So we've actually made a double bond. This is a double bond between carbon and oxygen. So oxygen is happy. And then the same thing over here. We've got a double bond in between this carbon and the oxygen. Oxygen is happy because it has 8 around it, and carbon is happy because it has 8 around it. And to highlight that a little bit more, I've put boxes around these so you can kind of see how to count them. Okay, so if we count around carbon, remember all these shared ones you get to count, there are 8 around carbon. Okay, and if you go to the oxygens, there's 8 around each oxygen as well. Remember, it takes 2 double bonds for this. Same thing is true for this one over here. 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electrons around this oxygen. Everybody has 8. Everybody's filled. Their valence shells are exactly the way we want. Okay? Now, there's another way that you can indicate bonds, okay? And instead of having all these dots around everything, you can use a line to indicate those shared electrons or a shared pair. Okay, this is called the structural formula, and this is probably what you've seen before. So remember, each line represents 2 valence electrons. So instead of drawing these dots here and here between the oxygen and the hydrogens, you can draw a line. So this structure, this Lewis dot structure here, is the same thing as this structural formula here. Instead of drawing these paired dots, we draw a line to represent a single bond. Okay, now you can't draw lines for these that are on oxygen because these aren't being shared between the oxygen and the hydrogen. These are the electrons that are already around oxygen that don't need to be shared. Remember, hydrogen only needs 2 to be happy. Okay, so just sharing that one little electron over here with the oxygen, these guys are bouncing back and forth. Hydrogen is happy with 2. Doesn't need these guys up here. So we only draw lines for the ones that are actually being shared in forming the covalent bond. We don't draw lines for any of the others. Okay, so let's look at some more examples. Here we've got hydrogen cyanide. Okay, this is hydrogen, carbon, and nitrogen. Alright, so carbon has 8 electrons around it, and the reason why it has 8 electrons around it is, remember, each line is worth 2 electrons. So we've got 1, 2, 3, 4 lines. 4 times 2 is 8. 8 around carbon. It's happy. Okay, now if we count around nitrogen, we've got 1, 2, 3 lines. That means 6 electrons and 2 dots for a total of 8. Hydrogen has 1 line, so that's 2 electrons. So this structure is happy the way it is, okay? And then we've got another structure down here that has 2 hydrogens in it. It has a carbon and it has oxygen in it. Everyone is filled and happy here, okay? And the way that we know that is we know that hydrogen has 2, okay? Each hydrogen has 2. If we count around carbon, there's 1, 2, 3, 4 lines, which means there's 4 times 2, 8 electrons around carbon. And if we count around oxygen, we've got 1, 2 lines. Remember, that means that we have 4 electrons, 5, 6, 7, 8. Okay, each line, remember, is 2 electrons. So everyone is content. All right, so how exactly can we represent these covalent bond structures? We can use different types of models, okay? There's the structural formulas where you have the lines that are just connected between them like this, okay? Very simple, easy to see your angles that things are drawn at, which you learn more about in chemistry, okay? Or we have a couple of other models. There's ball and stick models where you actually have little balls and that represent, or spheres that represent the different atoms, and they have different colors of spheres for different atoms. Hydrogen's always white, carbon's always black, oxygen's always red, and then there's other colors for other atoms as well, like chlorine is usually green, and that, or the halogens, everything in group 17 is usually green, and that sort of stuff. And again, you learn more about that in advanced chemistry. But it is very easy to see the angles between them when you have those ball and stick models drawn. Okay, the other type of model is the space filling model. So the advantage to the space filling model is it actually shows the atoms to the correct size. Hydrogen is very tiny in comparison to oxygen, so you get a better idea of what the water molecule actually looks like. I always like to call it Mickey Mouse because it looks like two little ears and Mickey's head. Okay, and it actually shows them kind of in the right place as well. Okay, you just can't see the actual bonds. So, last thing I have is just two visuals for you for glucose. This is the ball and stick model of glucose. Remember I said black is all your carbons, so there's 6 carbons on here, and I said red is always used for oxygen, so there's 6 oxygens on here, and then all the little white guys are hydrogens. And these sticks represent the covalent bonds, so you can think of those as 2 shared electrons in between here. Oxygen needs 2 more electrons, it's sharing 2 in here to be filled or happy. Carbon, remember group 14, 4 valence electrons, it needs 4 more to be happy, so it can make 4 bonds, 1, 2, 3, 4, to be filled. This is the space filling model for glucose. So you can't see all those bonds, but you can kind of get a better idea of what the real actual shape for glucose is, because this is how they actually fit together. Okay, so glucose doesn't look spread out like this for real. Glucose really looks like this. Okay, so that's the advantage for a shape filling model. And that is the end of the presentation about different types of bonding. As a review, remember ionic bonding is between metals and nonmetals, and it has it's always a transfer of electrons. Okay, covalent bonding is between nonmetals typically, and it is a sharing of electrons. And this one is our metallic bonding. And remember, metallic bonding is between metals. So that is it. That's all we're going over. And I hope that you got a lot out of this.